So this is lecture 18 on properties of continuous functions. So I'm going to run through a sketch of a few theorems that are important theorems to know about for continuous functions. First of all, I should remind you that we had a definition of a set being compact if and only if every sequence in the set has a subsequence which converges to a point in the set as well. That was also termed sequential compactness. And this is what theorem 3.4.1 says. It says if you have D, which is a non-empty compact subset of the reals, and f is a function with that compact domain to the reals and it's continuous, then the image of D under the function is likewise compact. In particular, that means that f of D, the image of D under f, is closed and bounded. Alright, so let's look at the proof of that. So he says take any sequence in f of D, right? Then for each n, that means that there exists an an such that yn is equal to f of an, and an must be is in D. But since D is compact, there exists a subsequence a sub nk of an and a point a in D, which a sub nk converges to a, right? And so then what? It then follows from theorem 3.33 that the limit of, let's see here, let me remind myself what it's theorem 3.33. My memory, my numerical recall of the theorem numbering in this book is not awesome. Let's see here. Theorem 3.33 was this guy. Let's see here, what we got. F function continuous at x naught if and only if every sequence which converges to x naught, the sequence of values likewise converges to the value of the limit point. Okay, great. So, all right, if and only if, right? So that gives us a way to test. Let's see here, the limit in terms of the corresponding sequential limit. All right, so let's see your limit of the subsequence y sub nk is the limit as k goes infinity of f of a nk, which is equal to f of a, right? Therefore, f of d is compact. Let's see here, right? Because we took a sequence in f of d, and we showed that there was a subsequence of that sequence, namely ynk, and the limit of that subsequence is in fact a value which is in f of a, which is in D. Good. And he says the final conclusion follows from theorem 2.6.5, which said that compact implies closed and bounded. All right. So, what we got next here? Definition. A function from D to R has an absolute minimum x bar if f of x is greater than or equal to f of x bar for every x in D. It has an absolute maximum if f of x is less than or equal to f of x bar for every x in D. So, like, here's a picture. Some function takes some values between a and b. The maximum is, apparently right about there. The minimum is right about there, right? So, like, I'm trying to say is you could think about this point right here as being that x naught, right? So if you pick another thing right here, like, at x, say that's x, right? Then you have f of x naught. Oh, and I said x naught. He's used x bar instead of x naught. My bad, x bar. You have f of x bar is greater than or equal to f of x. In fact, that's true for any x you can draw in there, right? So that makes that x bar the place where there's an absolute maximum, right? So let's see here. Where did my... Let me fix that. Fix that right there. There we go. Get out of there. All right, great. So next up, what can we do with that? Well, we can state the extreme value theorem. The extreme value theorem says that if you have a function which is continuous on a compact domain, then f attains an absolute minimum and an absolute maximum on D. Usually we use and. I usually say it attains, but whatever. I guess he's used this language and absolute max and absolute min. But anyway, let me not fuss over that. Oftentimes you hear people say that a continuous function on a compact domain attains its minimum and maximum on that domain, meaning that there exists a point, or a pair of points rather, in the domain for which the values at those points are larger than all the other values attained as you input other things, or smaller than in the case of the minimum. But okay, yeah. Anyway, since D is compact, A equals to f of D is closed and bounded, right? And so he mentions down here after the proof that this could be shortened by using theorem 2.6.4, but we're going to give a direct proof. Fine. So, all right. So I think theorem 2.6.4 basically says that if you've got a function that is let me look it up for a second here. Where'd it go? Theorem 2.6.4 says if a non-empty subset of the reals is closed and bounded above, then the maximum on the set exists, and likewise if it's closed and bounded below, then the minimum on the set exists. So the minimum on this set, the image set existing, would mean that there is a minimum for the function. The maximum for the image set existing would indicate that there exists an absolute maximum for the function, given the definition above. So really this is like once you have that the image is closed and bounded, it's like pretty much immediate from that. So you've got a function, it's continuous, it has a compact set, right? Domain is compact, then since it's compact, f of the image is closed and bounded, so at that point you could apply theorem 2.64 and you'd be done. So like this is more complicated than it needs to be, right? But this proof is given just to sort of add texture to the result, I suppose, try to explain the mechanics of it a little bit. That's, I think, the reasoning for this proof. So I'll go through it. Let M be the infimum of A, and so that means X, it's taking X in the domain, and f of X, it's sorting through those values, and the greatest lower bound of that. And so because of the, you remember that proposition characterizing the infimum, where if we take something that's the inf and then we add a little bit, then there has to be something between the infimum and the plus a little bit piece. In other words, 1 over n is playing the role of epsilon in the epsilon characterization of the infimum we looked at before. So in that sense, there exists an a sub n in A such that a sub n is between the infimum and the infimum plus a little bit. And great. So for each n, a sub n is in A, which is the image of D under F, which means that there exists an x sub n such that a sub n is equal to f of xn. And so actually we have this. We have that f of xn is squeezed between m and m plus 1 over n. And furthermore, by the compactness of D, there exists an element x bar in a subsequence x sub n k that converges to x bar in D as k goes to infinity, right? Because that's a sequence, there has to be a subsequence given the compactness. Given a sequence, there has to be a convergent subsequence by the compactness of D, right? And so looking at that squeeze relation, I mean this inequality here with respect to the subsequence, we get that. But of course, as k goes to infinity, m stays m, and this goes to whatever, but this also goes to m. So by the squeeze theorem, that limit exists and is also equal to m. So the limit is k goes to infinity of f of x and k is equal to m. But on the other hand, by continuity, we also know that the limit as k goes to infinity of f of x and k is f of x bar. So that gives us that m is equal to f of x bar. And also that, well, m is less than or equal to f of x by construction of m. Remember, m is the infimum of the set of images for f, so this is like from the construction of the set A. And so that shows then that x bar is the minimum of f on the set D. And I say the, but I really should say and minimum, a minimum. There could be more than one, of course, right? All these theorems about maxes and mins, for the most part, at least until we get to the end of this section, they're not unique. There could be more than one minimum. There could be more than one maximum. There could be, I should say more carefully, there can be more than one point in the domain at which the maximum value is attained. There can be more than one point in the domain at which the minimum value is attained. All right? But the absolute maximum value itself, that's unique. The absolute minimum value itself, that's unique. We could have different inputs which reach that same largest or smallest value. All right, corollary. Let me zoom in a bit. Corollary, if f from the closed interval of a to b is continuous, then it has an absolute maximum and an absolute minimum on AB. So this is from the fact that the closed interval from a to b is closed and bounded, and hence compact. So, yeah, there you go. And of course that is the bedrock principle on which the closed interval method rests on in Calculus 1, right? So, next up, we are working towards what's called the extreme, oh, excuse me, I'm an idiot. Back it up for a second here. The closed interval method is also sometimes called the extreme value theorem. Actually, I wouldn't use that. I don't know. I don't tend to say that, I don't think. To me, the extreme value theorem is a more general theorem, and the closed interval method is, well, the closed interval method. It's a specific application of the extreme value theorem, but the extreme value theorem is a general topological result. I mean, the extreme value theorem, to me, is the statement that a continuous function on a compact domain attains extreme values on that domain. That's true in one dimension. It's true in higher dimensions as well. Anyway, I will get over it. Let's go on here. So lemma 3.4.5, let f be continuous at the point C and suppose that f of C is positive, then there exists a delta greater than 0 such that f of x is positive for every x in the intersection of that delta ball centered at C and the domain D. And so in other words, what this is saying is that if your function is continuous and it's positive at one point, then if you're close enough to that point, it's going to stay positive. All right, like you can't have functions just willy-nilly, continuous functions just willy-nilly jumping from positive to negative. You know, like it's going to stay positive if you stay close enough to it. That's what this lemma is saying. So the proof is down here. So let epsilon be f of c, which is positive. By continuity of f, there exists a delta, such that if x is in the domain and x is within delta units of c, then the absolute value of f of x minus f of c is less than epsilon, right? So unwrapping that, let me unwrap this here for a second. This becomes, of course, minus epsilon less than f of x minus f of c less than epsilon, and then if you add f of c to that, this gives us that f of x is less than f of c plus epsilon, right? On the one side, and it also gives us that f of x is He says it's greater than, oh, add f of c then. We get f of c minus epsilon down there. Okay, fine, yeah, I got it. Right, from the other side we get that. Great. But f of c minus epsilon is equal to 0, right, because f of c was epsilon. And that's true for every x in the intersection of the ball of radius delta centered at C and D. So there you go. That's proof. Ah, cool. Very nice. And of course we can also prove the same. If f of c is negative, then it has to stay negative if you're sufficiently close, assuming the function's continuous, right? Like continuity gave us this estimate as it related to that constraint. And without this constraint leading to that estimate, we don't get to say that, right? So, theorem. And I want to say that this is sometimes called, I want to say this is Bolzanos theorem, but let me check on that right quick. One moment. Just a moment. All right, let me look it up. Bolzano. B-O-L-Z-A. All right. Well, that's apparently a city in Italy. That's not helping us. I'm looking for Bolzano theorem. Let's see here. Well, let's see here. Yeah, this is what Wikipedia says under their intermediate value theorem article. They say that a continuous function has values of opposite sign inside an interval, then it has a root in that interval. This is known as Bolzanos theorem. So Bolzanos theorem is saying, in short, that if you have a function that's continuous on a closed interval and it flips signs at the endpoints of the interval, right? In other words, f of a times f of b is less than 0. That says that either this is plus and that's minus, or that's minus and this is plus, right? If it flips signs in the interval, then it follows that there exists a constant in the open interval from a to b such that the constant's equal to 0. So, credit where credit's due. This is Bolzanos theorem. All right. And great. So here's the proof. So I gotta just make sure I'm in frame here. So Bolzanos theorem. Suppose, and so we'll assume that f of a is less than f of b and zeros between it. All right. He defines the set A to be x in the closed interval a to b, such that f of x is non-positive, right? It's either negative or 0. And this is non-empty, of course, since a is in the set and f of a is less than 0, right? Rather, I should say a is an element of this set because f of a is less than 0, right? So that means a has met the criteria to be in that set. So it's non-empty. And it's also bounded below because this is naturally a subset of AB, right? Because you're taking points from AB and then adding a condition to it, so it's immediately clear that that's a subset of that. And a subset of a bounded set is bounded. So in particular, A is bounded below since A is a lower bound. It's also bounded above since B is an upper bound. All right, anyway. So therefore, C equals to the supremum of A exists, and it has to, of course, also fall somewhere between A and B. All right, so we're going to prove that f of c is equal to 0 by showing that f of c is less than 0 and f of c is greater than 0. Both lead to contradictions. Very nice. I think that's the same proof that I have in my Calculus 1 notes. It's been a few years since I wrote those notes, but I know I have a proof of Bolzanos theorem in my Calculus 1 notes, and I think this is the proof that's there as well. Which I might well have found in Apostles' Calculus. Anyway, f of c less than 0 there exists delta greater than 0, such that f of x is negative for all x sufficiently close to c, right? And c is less than b because b is, because f of b is greater than 0, right? And he says we can find s in c comma b such that f of s is less than 0, all right? In particular, he says, well, let s be the minimum of c plus delta over 2 and c plus b over 2 if you want to know exactly how to do it, all right? But then this is a contradiction because s is an element of A, and s is an element of A. How do we know s is an element of A? F of s is, because f of s is less than 0, right? S is an element of A because f of s is less than 0, and yet s is greater than c. Why is that a problem? Well, remember c was the supremum, right? So we just found something beyond the least upper bound, which is also in this set. That's a problem because that means that c is not functioning as the least upper bound or the supremum of the set. So that's a contradiction. Great. And then, on the other hand, if f of c is positive, then the values of f of x have to be positive for all x sufficiently close to the intersection of the closed interval and the delta ball centered at c. And as such, a is less than c because, well, f of a is less than 0, right? And c is the supremum, right? So that means that a has to be less than, I don't see why a couldn't be equal to c. F of c is positive. Oh, it's because because f of c is positive, right? So, okay. So there exists t such that f of x is positive for all t in x and t comma c. And in particular, you can choose that t by taking the max of c minus delta over 2 and a plus c delta over 2. I think it's probably, it might be useful to draw a picture here. We'll try. So here's a, here's b. For the previous argument, c is the supremum of a, right? So let's, and a is what? A was f of x less than or equal to 0. So let's suppose that, this is the supremum of a. This is c, all right? And then, all right, let's see here. Delta greater than 0 such that c is less than b, right? Okay. He says let s be the minimum of c plus delta over 2. Remember the delta is chosen such that f of x is negative. So, let's see here, so c plus delta over 2, right? And c plus b over 2, well, that's like the halfway point. So it could be the deltas here, it could be the deltas like plus delta over 2 could be like over, it could be here, it could be over there. Great, but if we choose s to be the minimum of c plus delta over 2 and c plus b over 2, then how do I know? Let's see here. S is an element of C comma B. S is the minimum. Oh, okay. So, well, f of s is less than 0. Sorry, guys. I'm just thinking. It's probably clear. C plus delta over 2. I mean, f of s is less than 0. S and C comma. Well, I mean, the fact that S is in C comma B is apparent because, you know, if S is C plus delta, so the delta plus delta over 2, I guess delta plus delta over 2 could be beyond B. That would be a trouble. But definitely C plus B over 2 is not beyond B, right? So certainly the midpoint of C and B is in C comma B. And on the other hand, C plus delta over 2 may or may not be, but it could be. So the delta was given to us back here in order to insist that, like, f of x is less than 0. So f of x is less than 0. So I think there's cases to think about, like what happens if C gets, I suppose C could be, I don't know, So C delta, that's a, you know, that's something like, this guy is something like this, right? Now I've put my delta over 2 there, so fine. I guess it's like this. This maybe, right? That could be the ball centered at C of radius delta, right? It could extend past B in principle, I suppose. Could it though? I don't think it can, because we've given, that actually can't happen because we're given that f of b is positive and f of x is less than 0 for all the x in this ball. So like that's not possible even, right? Like my picture's not even, that can't even happen for the so constructed delta here. So yeah, let me undo that. Sorry guys. Basically delta has to, that C plus delta has to come in before B, otherwise you're in trouble. So but in any event, plus or minus delta from C, the values are negative, right? And so like f of s, that s there, whether it's the midpoint or whether it's plus delta over 2, that's negative. And that's a contradiction. The whole point was to construct an s which is larger than C, right? Because if s is in this interval, then it's clearly going to be not, it's bigger than C, which is the trouble, because C is supposed to be the least upper bound, and you've just found a value which is beyond, you know, which is in the set and yet larger than the alleged upper bound. That's a problem. And I think that the idea of the second part of the proof is very similar, right? If f of c is positive, there exists a delta greater than 0, such that f of x is positive for all x which is in the ball intersected with the closed interval. A is less than C because f of a is less than 0, so that means that a is not in this, can't be in such a ball because f of a is negative. And so that means that there exists a t between a and c, and he's just basically going to argue that contains a point which he's going to call t. Well, he calls it t. There exists this point t, which is going to be, you know, less than the supremum, and what's the problem with that? T is less than t prime, less than or equal to c, and f of t prime is less than or equal to 0. T is less than c. Well, anyway, I'm sorry. I'll stop wasting your time. You can, you can study this more carefully. I think it's clear, but I personally, I really have to write this stuff out and think about it for a while before I totally buy into it. But it's proof by contradiction too, so it's kind of like, I don't know. I can't get too excited about it. I'm sorry, just me. But intermediate value theorem then is essentially a corollary to Bolzanos theorem. So you have a function from the closed interval from a to b to r, a continuous function f of a less than gamma less than f of b. I usually use a big N for the intermediate value, but whatever. Then there exists a number c in the open interval a to b, such that f of c is equal to gamma. And likewise, the same conclusion if f of a is greater than gamma is greater than f of b. Another way to say this, if you're talking about it, is if gamma is in between f of a and f of b, then there exists c in ab such that f of c is equal to gamma, right? In between, that's a phrase you can use to include both cases, f of a less than f of b and f of a greater than f of b. In both cases, gamma is in between f of a and f of b. Anyway, moving on here. Here's a picture of it. So, gamma is this guy right here. And as you can see, it's in between f of a and f of b. And the intermediate value theorem says, hey, there's a c right there, such that f of c is equal to gamma. And there's at least one, all right? It could be, if they had a more exciting function, you could have stuff like this happen, right? Whee! And, in that case, your gamma might hit through more than one choice for C, right? We're not saying that the choice for C here is unique. It's just that there exists at least one, right? I mean, there could be multiple choices for that C. That's not a problem. That's just not really addressed by this theorem. Okay. So the proof is simple enough. It's basically to just use Bolzanos theorem. And so what you do is you let phi of x rather be f of x minus gamma. Then it's continuous because it's a continuous function minus a constant. And the product of phi of a and phi of b is f of a minus gamma and f of b minus gamma, and that is by construction that's negative because, remember, you have by assumption here f of a less than gamma less than f of b, or you have f of b less than gamma less than f of a. So like either you have f of a minus gamma less than 0 and f of b minus gamma greater than 0 in this case, or you have f of b minus gamma less than 0 and f of a minus gamma greater than 0. So this is either plus minus or minus plus. In either case, it's negative. And so then we can apply Bolzanos theorem to phi, So there exists a C such that phi of C equal to 0, but that is equivalent to saying f of C is equal to gamma. And the proof is complete. Cool. All right, corollary. 3.4.9, continuous function, then if m is the minimum and big M is the maximum of f of x, values taken from a, b, we know these exist by the extreme value theorem. And then, well, this says more. It says, in fact, every intermediate value between your min and your max is also attained. There exists a C such that f of C is equal to gamma for every gamma in there. Another way to write this would be that f of the closed interval a to b is equal to the closed interval m to m. So if you wanted to state this corollary compactly in terms of set theoretic notation, it's just this statement right here. And so these are some really nice examples right here. First of all, suppose you want to prove that the equation e to the x equals to minus x, has a solution. So great. Well, I'm not sure we've really built up the theory of the exponential function in this course. Oops. But we'll talk about it anyway. So the exponential is continuous. Of course, x minus x are continuous. And so the function f of x equals e to the x plus x is continuous because it's the sum of continuous functions. Now notice that, let's see here, f of, what's he going to do? F of minus 1 is equal to, what? E to the 1. Okay, fine. Right. Fair enough. Sorry, it's just bothering me the way he wrote it. I was like, what's he doing? Okay, he's just arguing that f of minus 1 is negative. Okay? And on the other hand, f of 0 is equal to e to the 0 plus 0, which is 1. That's positive. So that means somewhere between minus 1 and 0, there is a point such that f of c equals to 0, right? Because it changed from negative to positive on the interval. There exists a c in, oops, I zoomed in too much. My bad. There exists a c in minus 1 to 0, and I should say, open interval from minus 1 to 0, such that f of c is equal to 0, but that means that e to the c plus c equals to 0. In other words, e to the c is equal to minus c, right? In other words, that's a solution to the equation e to the x equals to minus x. E to the x equal to minus x has solution c in this thinking. Very cool. Now the next example, 3.42, he argues that there exists an nth root for any positive real number. So remember, by the binomial theorem, we have that this is greater than or equal to 1 plus na, because you're dropping a bunch of positive terms here. We're assuming a is positive. And of course then that's greater than a. Prove that in exercise 1.37. And so he says, okay, so consider the function f of x equals x to the n. F of 0 is 0, and f of 1 plus a is greater than a, right? So it must be that somewhere in the interval from 0 to 1 plus a, there's a intermediate value such that f of, and we'll call the intermediate value x in this case. So x is like c in our theorem. F of x is equal to a, because we have 0, f of f of 0 equals to 0 is less than f of 1 plus a. And I'm still not getting to the point here. I should put an a. Ah, curses. Sorry, guys. Let me think of where to write this and how to write it. All right. My apologies. So, um, 0 equals to f of 0 is less than a, which is less than f of 1 plus a. That's the inequalities. In other words, a is an intermediate value between 0 and which is f of 0 and f of 1 plus a. So that means that there exists an x between 0 and 1 plus a, right? Such that f of x is equal to a. That's the intermediate value theorem. But f of x equals to a means that in this context, x to the n is equal to a, right? And so that is another way of saying that x is the nth root of a, right? It's that positive fundamental root, if you will. And the reason I know x is positive is because, well, it's between 0 and 1 plus a. Now, what follows next is an alternative proof of the intermediate value theorem, which is based on bisection of the interval. And this is actually pretty close to a method for finding roots. You know, a similar idea can be used for root finding, where you just take the interval, look for a sign change, and then just like, if you find the sign change on the left, you zoom into it, and you just keep zooming and zooming and zooming. I think I went through a proof like this earlier in this course. But that's essentially what goes on here. He basically describes how to take the interval a to b and then to bisect it and either choose the left or the right interval, depending on where, you know, comparing the value of the midpoint and what happens relative to the intermediate value. So, let's see here. So, it says in the first case we set a2 equal to a1 and b1 equal to c1. In the second case we set a2 equal to c1 and b2 equal to b1. In other words, we're either moving down the right endpoint or scooching up the left endpoint, such that in either case we have that f of a2 is less than gamma is less than f of b2. So basically you're just conspiring to keep zooming down such that the intermediate value is still intermediate to the new subinterval. And then he just repeats this process again. Take the midpoint of a2, b2, and then pick a c2 such that gamma is still intermediate to f of a3 and f of b3, where a3, b3 is selected by either sliding the left or the right endpoints to the new midpoint c2, you know. And so you just keep going down, 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 always having gamma intermediate to the values. And so what you're doing then is you're constructing a sequence, a nested sequence, and this is the length of the sequence, bn minus an. You notice that it's b minus a over 2 to the n minus 1. As n goes to infinity, this goes to 0, so the length of the subintervals in the nested sequence is going to 0. And in every case, gamma is intermediate to an and bn. And so then you just go through the nested intervals theorem to say that, okay, so the limit as n goes to infinity has to be, the intersection of all those intervals is just a single point, c. And when you study the proof of that nested interval theorem, you also see that the an and the bn both limit to c, actually, as n goes to infinity. And then, likewise, by the continuity of the function, you have the limit as n goes to infinity of f of an is f of c, and likewise for bn. And so you then have, you could use a squeeze theorem to see that f of c is less than gamma, and gamma is excuse me, yes, f of c is less than gamma, but f of c is also greater than gamma. So what does that mean? I think I'm missing. How do I? Huh? How did I get to less than or equal to? Huh? Hmm. Oh, okay. So the squeeze theorem doesn't have to have equality in the squeeze in the inequality. You can, if you have strict inequality like this, then that limits to the same thing that limits to. It forces the middle one to exist and have the same limit. But of course, this is a constant sequence in this context, so like the limit of gamma is gamma. But on the other hand, the f of an and the f of bn both limit to f of c, so that forces gamma to be equal to f of c. Okay, and then finally, this section ends with a discussion of the one-dimensional inverse function theorem. Now, I'll talk more about this in the multi-dimensional context, higher dimensional context past this point. But here it is. If you have f as strictly increasing and continuous, and if c is f of a and d is f of b, then f is 1 to 1. All right. And indeed, f of ab is equal to c comma d. And also the inverse function from CD to AB is defined by f inverse of f of x equals to x, where x is anything in the closed interval a to b. That's a continuous function, in fact, from CD onto AB. So this is the inverse function theorem, which says that, in a nutshell here, if you have an increasing continuous function on a closed interval, then the inverse exists and is likewise continuous. So the proof is given on the next page. It relies on the intermediate value theorem. Let's see here. So how to prove f inverse is continuous on CD. Fix any y bar in CD in a sequence yk that in CD that converges to y bar, and let x bar be in AB and xk in a comma b such that those are how you get to f of, words here. Because of the construction of y bar, it means there has to exist an x bar such that f of x bar is equal to y bar. And likewise, there has to exist a sequence which has as its image the sequence yk. And then f inverse of y bar equal to x bar. He says, well, by the way, I skipped the first sentence here. He says the first two assertions follow from the monotonicity of f and the intermediate value theorem. In other words, because it's increasing, that gives you the one-to-one property, and the corollary to the intermediate value theorem said that. So, like the strictly increasing means that, in particular, it's very nice. It means that f of a is less than or equal to f of x is less than or equal to f of b for all x in AB, right? But what does that mean? That means that f of a and f of b are the min and the max. So remember that corollary, that if that's the min, that's the max, then f of AB is equal to f of a, f of b. So that's what's going on, and so how to say this? So I'm missing a word here. Strictly increasing and continuous. I mean, I do need to know that the function is 1 to 1 to find the inverse, right? once it's 1-to-1, then I know the inverse can be constructed. That's just set theory. So the fact that the function's 1-to-1 is pretty much immediate from this. If you have f of a is equal to f of b, it must be that a is not equal to b. Oh, but this was strictly increasing, right? Strictly increasing, so I've messed it up strictly. Yeah, because I was about to say, what about a constant function? No, strictly increasing, so we can't have equality here. If I can't have an equality, then I better make this for all x in the open interval. There we go. Anyway, the point is that the strictly increasing implies 1-to-1. And so since it's 1-to-1, we can find the inverse. And so that's the first sentence here. Now he's setting out to prove that the inverse is continuous. All right, that's what remains to show here. And so we got f inverse of y bar is equal to x by the definition of the inverse. And likewise, the inverse image of yk is xk. So he says, suppose by contradiction that xk does not converge to x bar, then that means that there exists an epsilon naught positive in a subsequence xkl of xk such that that subsequence is larger than or equal to epsilon naught for every l. But since the sequence is bounded, that there must be a further subsequence that converges to x naught in AB. So he says we'll call this call the new subsequence x sub kl. All right. Fine. It kind of bothers me a little bit that you did that, but whatever. Taking limits in 3.7, we get x sub naught minus x bar greater than or equal to epsilon naught greater than 0. All right, the limit over the new subsequence, right? But on the other hand, by the continuity of f, f of xkl converges to f of x naught, right? So f of xkl equals ykl converges to y bar as L goes to infinity, and it follows that f of x naught is equal to y bar is equal to f of x bar, but that implies that x naught is equal to x bar. And that contradicts 3.8. Let's see here, x bar. Suppose by contradiction that xk does not converge to x bar. So we had a subsequence x bar equal, x not equal to x bar. I guess that's the contradiction, because it was a sequence that does not converge to x bar, and this says that what was x naught again? X naught here was the subsequence which converged to x naught. Okay. Sorry, I'm just kind of slow today. And then finally, remark 3.411. Similar result. So basically, you can do something similar with decreasing functions, right? It's just for if you have a strictly decreasing function, then would you have something like f of the closed interval AB would be equal to something like f of b comma f of a, I think. It's decreasing, so it flips the endpoints for decreasing function. So anyway, a lot of important results in this section. I'm sorry if I haven't done a great job on the proofs today. I'm struggling here. I'm a little bit out of time, and I got to get this done today. So I hope you understand. It's important to understand the statements of the theorems. I think the place, like the easiest way to test on this section is with examples, with something similar to examples like 3.41 and 3.42. This is sort of the more natural way to test this section, right? Although, admittedly, like if I give you Bolzanos theorem and ask you to prove the intermediate value theorem, that's like not a bad test question, right? Or the easier version of the proof of the extreme value theorem, right? If I give you theorem 2.64 and ask you to prove this, then there are ways of taking the proofs in this section and making them into decent test questions if you put the right sort of on-ramps onto the questions. So anyway, I just thought I should say a little bit about that since your test is soon approaching. So thanks, guys.